All right, so this is actually round 2 of graphing rational functions example 5. I'm not sure what happened to the first one, but let's go with this. So the first thing I want to mention to you is the fact that this line is in the middle of your paper. You are going to have a blank sheet that looks just like this in order to graph your rational functions. This is what it'll look like that you need to turn in for your test. This is what it'll look like for the homework assignments you have to turn in. I have an extra line in the middle here because for some reason when I went to upload this document into the program I use, it put a line there. So just kind of ignore that and we'll just work with what we have here. Cool, okay, let's go ahead and get started. Okay, I zoomed in on the problem here, so this is the first problem that we're going to look at, and we're just going to follow the steps as we go through. So my first problem is f of x is equal to x plus 1 over a 2x squared plus 5x minus 3. Now, the first thing we want to look for are vertical asymptotes. And how do I determine if I have a vertical asymptote? Good. We're going to set the denominator equal to 0. And in this instance, we have a 2x squared plus 5x minus 3, and we're going to set that equal to 0, and you guessed it, we get to factor. So 2x and x with a minus in the back, you know your signs are different, so I'm going to have a plus 3 and a minus 1, because if you check your outsides and insides, you end up with a positive 6x and a negative 1x, giving me the 5x that we want in the middle. Cool. So now I know my asymptotes. When you set each of these sets of parentheses equal to 0, I'm going to have a vertical asymptote at x equals 1/2 and a vertical asymptote at x equals negative 3. Good. Let's go ahead and put that on the graph over here. I'll scoot this over. So we have 1/2 and negative 3. I'm actually going to make my graph a little bit bigger because it makes it nicer to work with, especially when you have something crazy here like this 1/2. It makes it nicer to work with. So 1/2 and negative 3. Okay, let's go to the next section here, a little horizontal asymptote action. So in order to determine whether or not we have a horizontal or a slant asymptote, we're going to look at the lead numbers. So if I have x on top and an x squared on the bottom, if the degree on top is smaller than the degree on the bottom, what does that tell you? Yep, we have a horizontal asymptote, so we can get rid of this slant part of it, and it's a horizontal asymptote at y equals 0. So if the degrees were the same, you would take the coefficients, but the fact that it's smaller on top, that's what gives you the horizontal. Good. Then the next question that we have is, does the function cross the horizontal asymptote? Now, anytime something crosses or it has the same value, it's equal. So what we're actually doing for if the function crosses a horizontal asymptote is we're going to set our function equal to that horizontal asymptote. So if we set it equal, in this instance, our asymptote is 0, and we have our function here of x plus 1 over 2x squared plus 5x minus 3, and that's going to equal my horizontal asymptote. Now notice, if your horizontal asymptote was something other than 0, then that number would change. But because it's 0 is my horizontal asymptote, we put that in there. So, in order to solve a rational expression, you multiply both sides by the denominator. So in this instance, it's 2x squared plus 5x minus 3. Those cancel, and I'm left with x plus 1 on the left, and 0 times anything, still 0. So now I have x plus 1 equals 0, so solve for x, and you get x equals negative 1. Da-da-da-da-da-da! We actually have this crossing. Because I have an actual x value here, that means my horizontal asymptote and my function have the same value when x equals negative 1. So I know that this crosses the horizontal asymptote at x equals negative 1. Let's put some stuff on our graph. So the first thing I'm going to put on my graph is my horizontal asymptote at y equals 0. I'm making my line a little bit thicker simply because it's going over that axis and I want to make sure that you can still see it. Otherwise, I wouldn't make my line so thick there. So we'll put it back to normal here. And I know that my graph also crosses the horizontal asymptote at -1. So I have my point, let's do a different color. I have my point here when x is equal to -1 and at the horizontal asymptote. Cool. Now, let's answer some more questions. So the next thing we're going to look at here are our intercepts. And anytime you have any equation out there ever and you want to find an a y-intercept, that is when you have a 0 for the x and a number for the y. So if I plug a 0 in for the x, I have f of 0 for my function. So 0 plus 1 over 2 times 0 squared plus 5 times 0 minus 3. So f of 0 is a -1/3. Cool. So now I know I have a y-intercept at -1/3, and I have an x-intercept. So you get an x-intercept when you have some number for the x and a 0 for the y. So if y is 0, then you have your function equal to 0. And we literally just did that over here because my horizontal asymptote had to be 0. But I also want to point one more thing out. So check this. If I have x plus 1 over a 2x squared plus 5x minus 3 is going to equal 0, and this one will always equal 0. When you multiply both sides by your 2x squared plus 5x minus 3, 2x squared plus 5x minus 3, that cancels, and I'm left with x plus 1 equals 0. Basically, anytime you want to find an x-intercept, really all you're doing is you're setting your numerator equal to 0. Oops. Because the denominator will always cancel out. And because it's set equal to 0, anything times 0 is 0. So really you're just setting your numerator equals 0. I'm good with you solving these either way. So now I get x equals -1. So I have the point -1, 0 for my x-intercept. Let's go put these 2 points on our graph and see what happens. So we now have the point 0, -1/3 for the y-intercept, and we already have our x-intercept on our graph technically because it's the same place that it crosses our axis. So check this out. I'm going to make my graph my pen here a little bit thicker. Your graph is drawn toward the asymptotes. So when you remember when we were talking about asymptotes, and the definition of an asymptote is it may cross. So you can cross a horizontal asymptote one time and only one time. So because my graph does cross the asymptote here, I'm crossing my horizontal asymptote one time, and then I am being drawn toward those other 2 vertical asymptotes. The only time your graph will ever cross this horizontal asymptote is right at this place. Notice I have a whole bunch of free space on the left and a whole bunch of free space on the right. This is why we have extra points. So our extra points are going to go in those spaces, so we'll have to come up with them. And remember, this is a function. So I need to know, is my graph going to be on top or on bottom? Why can't it be both? Yep, because if you go through and you make a vertical line for your vertical line test, it would cross both times. So in order for this to be a function, and this is a rational function, in order for it to be a function, it can only be on the top or the bottom. Okay, cool. I'm going to erase these and we're going to come up with some extra points. Okay, the first thing we want to talk about when it comes to extra points is what are we going to do for our extra points? So if you look at this graph, I want to find something to the left of my asymptote and to the right of my asymptote. Just like in the polynomial functions where we filled in around the x-intercepts, for rational functions, we're going to fill in around the asymptotes if I have blank space. So I'm going to use a nice easy number here. I think I'm just going to go with -4. And then over here, because 1 is so close, I'm going to actually come out here to 2. And honestly, extra points are just whatever you want to grab. So I'm going to try -4 and 2, and then let's plug those into our function and see what's going to happen there. So I'm going to plug these values into my original function and see what we come up with there. So my original function here was going to be f of -4 equals -4 plus 1 over 2 times -4 squared plus 5 times -4 minus 3. So f of -4, if I simplify this, will be -3 over 2 times 16, because remember you do exponents first, minus 20 minus 3. So f of -4 is -3 over 2 times 16 is 32, minus 23 is going to give me what, a 9? So I end up with -1/3. Check my math on that, make sure I did it correctly. Now let's plug in that 2. So if I have f of 2, I get 2 plus 1 over 2 times 2 squared plus 5 times 2 minus 3. So f of 2 is 3 over 8 plus 10 minus 3. So 3/15 is 1/5. Cool. So I now have the points -4, -1/3, and 2, 1/5. Let's put those on our graph. Okay, so I have -4, -1/3, and 2, 1/5. Now your graphs for these are smooth and continuous graphs. Because that's all the points I need, I know this graph is now going to be in the bottom, and because the point is up here, my graph is going to be up here in the top. So let's go ahead and draw that in. And these are nice and smooth, so you want to curve your graph. These do not need to look like L's. Now, so let's try to make this go up with a curve and down with a curve. The stylus doesn't always make it that easy to do, but I think we've kind of got it here. So this is curved down here as well, and that's our rational function. And it passes the vertical line test. It only crosses the horizontal asymptote one time. And we are in good shape there, people. Notice all this awesome work that we did for this problem. This is what you need to be showing on your papers. Now, you're not necessarily always going to have all of these extra points. It just depends on how many empty spaces you have around your vertical asymptotes. If you don't have any empty spaces, you don't have to worry about extra points. You may have multiple empty spaces that you need to worry about. So just think about that as you go through and graph these. Great job.